The universe is a busy place. It is full of galaxies. Each galaxy is a city of stars, gas, and dust. But what powers these cosmic cities? Sometimes it is the gentle birth of new stars. Other times, it is something far more violent. A supermassive black hole at the galaxy's heart can roar to life, outshining all its stars combined. We call this an Active Galactic Nucleus, or AGN. We recently pointed our telescopes at a distant galaxy, J1601-3113. We wanted to know what was happening inside it. Is it peacefully forming stars, or is a monster awake at its core? To understand a galaxy's secrets, we must learn its language, and that language is light. Specifically, it is the language of emission lines. Imagine a gas cloud floating in space. If you heat that gas or zap it with powerful radiation, its atoms get very excited. An atom is made of a central nucleus with electrons orbiting it. When energy is added, an electron can jump up to a higher orbit, a more energetic level. But it cannot stay there for long. The universe prefers things to be in their lowest possible energy state. So, the electron will quickly fall back down to its original, more comfortable orbit. When that electron falls, it has to release the extra energy it absorbed. It does this by spitting out a tiny packet of light, called a photon. Here is the crucial part. The energy of that photon, its specific color, is precisely determined by how far the electron fell. So, we have these two different barcodes of light, one for star formation and one for an AGN. How do we tell them apart? Simply looking at one emission line is not enough. We need to compare them. This is where the genius of the BPT diagram comes in. Named after Baldwin, Phillips, and Terlevich. This chart is one of the most powerful tools in extragalactic astronomy. It is a simple graph, a scatter plot. But it is designed to cleanly separate galaxies based on what is making their gas clouds glow. It acts like a cosmic sorting hat, telling us which galaxies are powered by stars and which are powered by black holes. Let's build the BPT diagram step by step. It has two axes, a vertical one and a horizontal one. Each axis is a ratio of the strengths of two different emission lines. A ratio is just one number divided by another. The vertical axis compares doubly ionized oxygen, O3, to hydrogen H-beta. The y-axis is O3 over H-beta. The horizontal axis compares singly ionized nitrogen, N2, to H-alpha. The x-axis is N2 over H-alpha. Now, let's return to our galaxy, J1601-3113. We collected its light. We measured the strengths of its key emission lines, the oxygen line, O3, the nitrogen line, N2, H-beta, and H-alpha. The next step was simple arithmetic. First, O3 divided by H-beta for the vertical axis. Then, N2 divided by H-alpha for the horizontal axis. With these two numbers, we had a coordinate. We had the precise location where J1601-3113 would land on our cosmic map. It is like having a latitude and a longitude for a ship on the ocean. We plotted the point. We held our breath. Where did it fall? The result was unmistakable. J1601-3113 did not land anywhere near the comfortable, crowded arm of star-forming galaxies. It landed high up and to the right, deep within the territory reserved for active galactic nuclei. The O3 over H-beta ratio was high, signaling highly ionized gas, a hallmark of hard radiation from an accretion disk. Combined with a high N2 over H-alpha value, it matched the classic signature of a Seyfert AGN. The location was not ambiguous. It was squarely in the Seyfert region. A single piece of evidence, even a strong one, is rarely enough in science. We must always consider alternative explanations. Could something else mimic the signature of an AGN? Could there be an imposter? One major alternative is shock waves. Huge outflows from the center or colliding galaxies can drive shock fronts that heat gas to millions of degrees. Shock-heated gas can also produce strong, high ionization emission lines. Energetic collisions in hot, compressed gas can strip electrons just like high-energy photons do. Powerful, widespread shocks could move a galaxy away from the star-forming sequence and toward the AGN region. Some versions include a third region, the liner zone, low ionization nuclear emission line region, often linked to weak AGN or shocks. Shock-dominated galaxies tend to show strong low ionization lines but lack the extreme O3 strength of classic Seyferts. For J1601-3113, the position was not in the liner shock zone. It sat firmly in the pure AGN part of the plot. The specific balance of line ratios, especially very strong O3 relative to hydrogen, is the classic signature of photoionization by an accretion disk. Good science requires cross-examination. The BPT diagram is a fantastic tool, but it is not the only one in our toolkit. If there really is a supermassive black hole actively feeding at the center of J1601-3113, it should be producing other signals. One of the most important of these is X-rays. The accretion disk gets so hot that it glows intensely in X-ray light. Stars and star-forming regions produce some X-rays, but a powerful AGN produces far more, especially hard X-rays. So, the next logical step would be to check for an X-ray source at the core of J1601-3113. If we detect a bright, point-like source of X-rays right at the galaxy's center, that would be smoking gun evidence for an AGN. It would strongly corroborate what the BPT diagram is telling us. We can also look in radio. Some AGNs launch colossal jets that glow brightly in radio light. Finding jets would be another strong piece of evidence. Finally, high-resolution spectra can reveal broadened emission lines from gas moving hundreds to thousands of kilometers per second, a telltale sign of the tumult near a supermassive black hole. So, we have identified a likely AGN in the galaxy J1601-3113 using a BPT diagram. Why does this one galaxy matter? Because every galaxy we classify helps us understand the grand life cycle of all galaxies. Understanding the balance between star formation and AGN activity is one of the biggest open questions in astrophysics. These two processes compete for the same fuel, the galaxy's reservoir of cold gas. When an AGN switches on, it can launch powerful winds and radiation that heat and blow out gas, shutting down star formation. Quenching. The AGN acts like a cosmic thermostat. We see a tight link between black hole mass and bulge mass. They grow together. AGNs are the active phase of this growth. J1601-3113 is another laboratory for this deep connection. The universe is a vast tapestry, and every thread is important. By using simple but powerful tools like the BPT diagram, we can unravel these mysteries, one galaxy at a time. The journey of discovery continues.